So now we are honored to have with us Shlomit Beker from the Albert Einstein College of Medicine, and she will talk with us about neurophysiological readouts of rigidity.
Can you hear me? Okay. Thank you very much. And I would like to thank Ilan and the people from the Israeli National Center for Autism and Neurodevelopment Research for inviting me. My name is Shlomit Beker, and I'm coming from the Albert Einstein College of Medicine, where I recently finished my postdoc. And I want to start with a short video. Let's hope the audio is working. What you just saw now is the first mobile application implementation to quantify rigidity in autism through finger tap. I'll get back to it in a few slides. So as most of you know, the two major diagnostic criteria of autism relate to interaction with the environment. So the atypical social interaction includes awkward communication, and they lack the typical back and forth type of communication. And the rigidity of routines, which I'd like to focus on today, includes repetitive behaviors, inflexibility, and insistence on sameness. Okay. Yeah. All right. Ideally, we want to be able to easily assess objective measures of biological readouts that underlie these diagnostic criteria. The goal here of my study is to gain a mechanistic understanding which, together with clinical assessment, can be used in the long term to define biomarkers for autism. We measure synchronization of neurooscillations. You know, we all know that the neuronal activity fluctuates all the time, okay? So it moves between up and down states. And it becomes more or less synchronous under different circumstances. For example, when we entrain to external rhythms in the environment, when we anticipate events in the environment, and when we attend to events in the environment, the neurooscillations become more in synchrony. Flexible synchronization is necessary for interaction with the environment, and thus it might be critical in ASD, where rigidity is an issue. I want to show you a few results from the study that I made. So this is a study on children with ASD. There are 31 children with ASD, age 6 to 9, and typically developed participants. And what they saw was a gamified task with 4 consecutive visual stimuli, followed by an auditory target. So the EEG, and we measured EEG. So what you can see here below these stimuli, I don't know if you can see my mouse, but what you see is a low-pass filtered EEG signal, average per each group. So as you see in the black line, this is the average for the controls. You can see the oscillations, okay? You can see the oscillatory pattern. In the black. In the pink, which is above it, and this is the average for the ASD group, you don't see, on average, this oscillatory pattern. To measure the phases, okay, I compared the phases between the groups. So the phases is where on the oscillation the stimulus arrives, okay? So ideally, if the participants are really entrained and locked to the timing of the stimulation, the phases will be very similar. So this is the case for the control group. The phases are very similar for the participants. However, for the ASD, it's more all over the place. It's not concentrated. It could appear in many different phases on the oscillation. And just to show you an example from two representative participants, on the left, it's a typically developed participant, and each line here is one trial. I don't know if you can see, but there is a black average. And on the right, it's an ASD child. And you can see that the average of the control has the clear oscillatory pattern across all these trials, but it lacks here in the ASD participant. Okay, so this was a study on children. With adults, and it had to be very simple. These are pretty young children, and they were sitting with the EEG cap for a long time, doing a cognitive task. So it had to be very simple. Here, in the adults, we could present more sophisticated conditions and to test the system. So in this study, I wanted to show them, to give them conditions with different levels of certainty and predictability. So this is the visual stimulus. It rotated in different rhythms for each condition. So I'll move from the top to the bottom. So here on the top, it's a fully periodical rhythm. So the visual stimulus rotated in fixed times every 666 milliseconds. In the second row, it's semi-periodic. So again, on average, it appeared every 666, but we added a Gaussian noise to it. So there was a jitter, a small jitter in this condition. Here in the third row, it's very similar to the second row, but with a larger Gaussian, so a larger jitter. Again, on average, it appeared every 666 milliseconds. And here at the bottom is the condition that I call random, because the stimulus could appear anywhere between 170 and 1150 milliseconds, and there was no sense of predictability when the stimulus arrives or when the stimulus rotates. In the middle here is the EEG for each group. The red is ASD, and the black is TD. And on the right is the frequency analysis done by Fourier transform. And it was done in order to extract the most significant or the most relevant frequencies in the brain. So I focus here on the 1.5 hertz, which is the stimulation frequency, right? On average, 666 milliseconds translates to 1.5 hertz. As you can see here, in the fully periodic condition, there was an equal power for both groups at 1.5 hertz. At the jitter conditions, both the small jitter and the large jitter, there was a significant difference between the power at 1.5 hertz. And at the random condition, there was again no difference between the group because there was no power. There was no sense of periodicity. So in other words, in the two extreme conditions, okay, the fully periodic and the non-periodic at all, there was no difference between the groups. But in the semi-periodic, where there was some, they needed to have some averaging or some prediction, even though it had a noise, only the people, the controls participant could do it. But it wasn't the case for the ASD. Okay, so again, we're trying to point to a possible readout of rigidity from the neuronal activity. And we found that temporal dynamics of the neurooscillations are altered. So both children and adults with ASD show reduced synchronization with rhythmic events. Sorry. Yeah, when the rhythm is jittered, however, rigidity of the ASD is then exposed. But this is not the end of the story. And many studies from the recent years show that the temporal dynamics, not only from the brain, but also from the body, are critical for cognition and also for social interaction. So studies, especially from the recent 5 years, both show that the temporal dynamics of cardiac activity, respiration, pupillometry, and skin conductance are super critical for perception and also when we interact with others. So there needs to be some synchronization, both between people and between a person and an external stimulus. Now, given the two diagnostic criteria of autism, of interaction with physical object and with other people, this is very critical in, could be critical in autism. However, it wasn't systematically investigated. So to put it in a context, my aim is to test this brain-body environment triad, where I want to test if the synchronization between the brain and the body with the social and the physical environment is impaired. So I showed you some evidence for the brain and the physical. And the next goal was to see if there is any impairment in synchronization between the body or the periphery and the physical. And as a first proxy of the synchronization, we built an app. So starting 2020, following the challenges in recruiting participants due to the coronavirus, we started to roll the idea to extend our lab experiment and to develop a mobile application for behavioral experiment with the idea of reaching people at their natural settings from a broad range of individuals without the need to bring them to the lab. We had two aims here. First, we wanted to, as I said before, to test periphery or motor synchronization, as, by the way, was done by Merav Achisar group, but not in a mobile application. And the second was to combine it with a clinical assessment. So we wanted to assess autism-associated traits and to include a questionnaire that was validated and has shown variability in responses also in typically developed. And for this, we chose the social responsiveness scale. Okay, let me show you how it looks like. Okay, so here's a demo of the clinical questionnaire. They're given some instructions, and then there is a calibration. And then we ask some demographic questions. It's self-paced, okay? So the participant is tapping on the screen for the correct answer. And then we include the full scale. It's a 60-item questionnaire. Sorry, the full questionnaire. Okay. Okay, and again, I'll demonstrate you how it looks like for the auditory domain. Okay. And the visual. And okay. To complement it with a full environment, we included, we built a website to communicate it with the participant. We give them information about this task, about the science behind it, about other studies that are done that are relevant. They can download the app. And we have some preliminary results. This is only TDs, only typically developed for teen. And what we show here is a replication of the study done by Vishne et al. From Merav Achisar group. And we just see here that there is an adaptation to changing rhythms. Okay, so it's not, we don't have here yet an ASD to compare to, but this is a first step. We also managed to recruit some participants. We have 5, up until last week, 5 ASD, 5 unaffected siblings. Again, it's too early to come up with any conclusion or any interpretation, but it's getting there. And having in mind that we aim to develop effective biomarkers, test reproducibility is critical. So for this, in a separate study, we tested how reliable EEG and behavior from children with autism is over time. So participants with ASD came to the lab. There were 33 participants in 2 separate times with up to 9 months apart. And they did exactly the same tasks, which include which include cognitive tasks. We measured EEG and performance. Out of 24 measures, which include visual evoked potentials, auditory evoked potentials, reaction times, variability of reaction time, heat rate, and so on and so forth, there were 10 that crossed the test for reliability. Okay, so it's intra-class correlation coefficient, and 10 were approved to be good. This is just an example of how the reaction time looked like in test 1, test and retest. Correlating it with the questionnaire, we found, okay, so we calculated a similarity index for each child to see how well they are similar, how similar they are between test 1 and test 2. This was correlated, this index was correlated with procedural IQ. And this is very interesting and even surprising given the high variability within participants, as Ilan Einstein showed and others, that exist in many measures. So it was shown for MRI, for fMRI. These are 2 examples of the studies that I've done that I showed it. So this is reaction times and how it's variable. There is higher variability for the ASD. This was done in the MOBI. So these are people with ASD that were walking on a treadmill, and they had higher variability of stride length compared with control. So it's another measure, it might be motor, that shows higher variability among the ASD. Okay, to conclude. Inflexible synchronization with the environment is indicated in ASD using EEG. Test-retest reliability sets the ground for developing biomarkers in the future. And measuring interaction of the body with objects and with other people is needed in order to establish the brain-body-environment triad in ASD. The take-home message is that rigidity of routines might be a clinical manifestation of an inflexible synchronization with the environment. And with this, I'd like to end. I'd like to thank my group, the Cognitive Neurophysiology Laboratory in New York, and my postdoc mentors, all the participants and their families, and thank you for listening.